So let's wait until 8:15. If the current comes, let's continue. If not, they'll turn on the generator. So the ACs won't work. So let's see, if we are lucky, we can continue the class. If not, we have to shift to the small hall. Okay, good morning, everybody. So, we are going to start the paper class. So, first of all, online students, can you hear me? Check it. Is uh, the audio good or is it lagging? Just let me know soon. Can you see the board? Nilomi Nayak, can you drop me a WhatsApp message if you can hear me? The text. Can hear me if the whiteboard is, you can, the smart board not flipped because chat here is not getting load. Think small problem in also. Okay. Something's online students. Can you hear me now? Okay. Online students, just tell me if you can hear me. The audio is clear, not lagging. Can you see the smart board? Can you? No. Okay. Right. So, if there's any issue, just let me know. Okay. If uh, the meeting got stuck, or if you ended up the meeting, or if the meeting is getting lagged, just drop me a message from WhatsApp. Okay. I'll be looking the chats. Right. All right. So today uh, is the paper class. So today we are going to discuss the practicals that's remaining. So until now we completed the main theories related to the measurements practicals. Okay. We completed the vernier caliper instrument separately, and now we are going to move on to micrometer screw gauge. Okay. Right. So take your tubes. Online students, I'll put the tube to the group. You can take it. micrometer screw gauge. Right. Okay. So if we move on to micrometer screw gauge, micrometer screw gauge, micrometer screw gauge, screw gauge. Okay. So this is the name of this instrument. Okay, screw gauge. So in this instrument, we use the screw principle to move the parts of this instrument mechanically, but to take the readings, we use the circular vernier principle. Vernier principle, I said that you have two parts, linear vernier principle as well as circular vernier principle. So to take the readings, we are going to use the circular vernier principle. To use this micrometer screw gauge, we are going to use the screw principle. All right. So now take the practical tube. If we move on to this micrometer screw gauge, it is sort of like this. You have something like this, like a horseshoe magnet, and you have a handle here. Okay, I view a skeleton system to this instrument is going to be like this, just like a spoon. Okay, and the main parts here is you have to know, you have to remember, you have a small part here, main part. Okay, and this green color part here can move where, like in vernier caliper, you have a moving jaw. This micrometer screw gauge has a moving jaw. This green color part can move in this direction, only in this direction. Okay, so how does this move? You have this blue color part here has some like this shape gimbals, so you can rotate this. Okay, you can grab this and you can rotate this like a screw. Okay, when you are rotating this, what happens? This green color part goes towards the pink color and goes away from this pink color. So you have to know the principle of a screw. Okay, the screw nut. We have this screw like this. So have you all used a screw? Okay, how does you tighten a screw? Put the screwdriver and rotate it in this direction, which is this direction, to tight a screw. When we tight a screw this direction, you will have a pen. Just take the nib of this pen, you can remove it. So to remove that, you have to turn in this direction. So I'll put R here to remove this T to tighten. So to tighten, in the sense, it's going inside that hole. If you have a hole, it's going to go inside. Understand? So if you are turning this in T direction, what do we call this direction? Something rotating in this direction, like this. In a flat surface, something is going to rotate in this direction. How do we mention it? Clockwise. Okay, you'll know a clock. How does the hands of a clock move? Like this. You have 0, 1, sorry, here you have 3, 6, 9, and you have 12. 0. Fine. So this is going to move like this. So this direction is known as clockwise direction. What? The clockwise direction. Clockwise. Clockwise. Okay. So now I'm not going to mention this T. I'm going to use the word clock. Okay. Clockwise direction. Fine. Right. So if something is going to be, if we are going to rotate it in the next direction, opposite of the clockwise, how do you call that direction? Anti-clockwise direction. Fine. So anti-clockwise, in the sense, students, we can call it in two parts. I mean, we can call it anti-clockwise, or how? What's the next name? Counterclockwise. Okay, counterclockwise. So you have to remember both of these names, because
sometimes in the paper they can tell you like anti-clockwise, or they can mention it as counterclockwise. I'm going to mention here counter clock or anti-clock. Okay, understand? So these are the two names of this R direction, right? So okay, so fine. Now this is counterclockwise or anti-clockwise, clockwise. Okay, so now I'm going to write in another color, yellow color. You are going to turn it clockwise. It's going to go inside or outside, towards the whiteboard or outside from the whiteboard, towards the whiteboard. Okay, towards, let's this is whiteboard. Okay, towards the whiteboard. I'm going to write words towards if towards paper artboard, it's going to be towards the mark. Okay, if you are going to turn it clockwise. Okay, right. So if you take this nib, take a nib and turn it counterclockwise, then it's going to get come outside. So it's going to be what? Outwards, not toward. It's towards. It's going. So we call it out. Okay. So how to remember this? Which is good, clock or anti-clock? Clock. Okay, clock is good. So it's going to be towards. Towards in a sense, it's going to be. If you take these two conditions, going inside is better to a book, but coming outside not good. Okay, then we are not focusing the book, just generally. Okay, so likewise you can remember that you think like a small kid, going inside a book is good, therefore clockwise is also good. Those two are the things that this is trick that you can just silly stuff. You just forget any case, you can remember like this. Okay, so anti-clockwise or counterclockwise is going to be the opposite of it. It's going to come outside. Okay, right. So again, if you want, if that book thing is not good, you can think about a pen. So if you turn turn it anti-clockwise, the pen is going to get disintegrated. It's going to break down. So that's not good. We can't use the pen. So counterclockwise, it's going to come outwards. If you going to turn it in clockwise direction, it's going to get tightened up, so we can use the pen. Okay, you have to much clear about this, because not only in this lesson you are going to come into the part magnetic field. Can you remember right hand rule, right hand grip rule, left hand rule? When you're doing electromagnetic what current or something, I remember in all levels, right? So you have to uh, keep these in mind, okay, without getting confused. All right, right. If you, in any case, if you forget these stuff, you the exam you're taking a pen, right? So you can turn the pen and you can get remember. Okay, right. But in some cases, okay, like we take the percentage. Good. Let's take white color again. White color. Okay. Take this screw principle. 99% of mechanical devices use this principle. 99%, everything. But some devices opposite principle. That means of that. If we turn it clockwise, it's going to come out. Now, generally, if we turn it clockwise, it's going to be inside. Turn it anti-clockwise, it's going to come outside. But in some cases, this 1% of mechanical device is going to do the opposite of this screw principle. If you're going to turn it clockwise, it is going to come outside. If you're going to turn it anti-clockwise, it's going to go inside. For example, you have a stand fan, stand fan, right? In your home, stand fan, you have the wings here. So you have a knob here, okay? That knob here is going to work in this anti-screw principle. anti-screw principle. Just turn that knob clockwise, so it won't get tightened. This will get loosed. It will come outside. Okay, so only 1%. So don't tell the next time when you are going to disintegrate a fan and tell sir that your screen principle is not working. I said now, screw principle, there's going to be 99 guesses. You take a lot of mechanical devices, 99% of those devices is going to have the screw principle. Only 1%, not to be exact, okay, this is not absolutely correct, almost a lower percentage of mechanical devices is going to have the anti-screw principle. Anti-screw. Okay, so I'm going to tell about my life. When I was doing O levels, I didn't know this counter word. I thought counterclock in the sense that's the same as the clockwise. Counter is going to be opposite of clockwise. So if there's anything like anti-counterclockwise, that's going to be clockwise again. Okay, there won't be any word like that. So you have to be clear about the things. Okay, now let's go again in if you want, you can write this down in your book. I'm not giving this cute because this is filter measurement. The general age part. So I'll erase this 99. If you want, I can write. No, I think so. Now let's look in the micrometers. Okay. Now I'm going to turn this in this direction. Okay. So this direction in the sense, if I can recall your O-level memory, I'm going to mark here like this. Sorry. I'm going to mark here like this and mark here like this. Do you know this symbol? What's this? This into the paper, this outside the paper. How you can remember this? If you take an arrow, those edges, the arrow was like this. Arrow is like this. So if you take this arrow like here and if you turn it like this, the front view, side view is going to be something like this. So the arrow is going to come in this. If you're going to turn this arrow like this part is going to be, if I drew it in a three-dimensional way, it's going to be like there's going to be like this. There's something here. It's going to be a sort of like that thing. Okay, so if you look from here, if you keep your eye level here, it's going to be in, so the arrow is going in that direction. So I'm turning it like this. Okay, understand? I'm turning it like this. So this is what direction? Clockwise or anti-clockwise? I turned like this. Clockwise. I'm turning it clockwise. So clockwise in the sense this is going to move which direction? This direction. Okay, if I'm going to turn it in the opposite of this cross comes here, this dot goes here. So I'm going to flip these two. This is going to be in the next direction. Okay, you have to remember that. Fine. So we know the parts. This is not going to move. Green part is going to move. This blue part is going to turn. Right. So these are steel parts. They manufacture this instrument using steel. Why do they use steel? Can't they use iron? Just ferrous. You know, iron. Pure iron can't they use it? Can use. Thing is, it's going to react with oxygen. It's going to get reacted with oxygen, and it's going to get rusted. So, purpose of this is not going to be that much good. So now I'm going to erase these parts. You don't need this. Right. So green color I'll keep here. I think you need this arrow mark. This blue color is going to turn. This is going. Fine. Everything is fine by now. Okay. Now I'm going to tell a small part. So this is an instrument. Why do we use this? Take a measurement. So this is a mechanical, not a digital device, right? Mechanical device. So since this is a mechanical device and we are going to take a measurement, there should be a scale here. A scale. So like I said before, there is a scale here and there's a scale here too. Okay. A scale like this, and a scale like this. Okay. Right. Two scales. Why do we have two scales? One of that scale is going to be the main scale, and the next part is going to be the vernier scale. So if we have two scale, we can take a measurement less than how many millimeters? 1 millimeter. Then if you have a two scale in one device, you can take a reading less than 1 millimeter. Fine by now. So have two parts, right? Now if you see, I drew these two in white color. So you can't take an idea. So what if I drew it like this? Tell me. Yes, I use this green color and I draw this thing. Okay, I draw this thing and color it up. Okay, yep. And I'm going to use a black color over this, and I'm going to mention like this. To mention this is a scale. Well, this part is a scale. That colored green color part is shaded part is scale. A scale. Now I'm going to draw this. All right. I'm going to draw this part in color and color it like my hand. Okay. All right. Blue color. So I'm going to mark that color going to be a, okay. So these scales are in vertical direction, as in the horizontal direction. How about a vernier caliper? If you take the main scale, that's going to be like this. Vernier caliper like this. Keep the vernier caliper like this. Vernier main scale is going to be like this, and if you take the vernier part, that's also going to be like this. The scales, both those scales are in vertical directions. But in this micrometer screw gauge, main scale in the sense this green color scale. Okay, now I'm going to tell you that green color scale is the main scale. I'll tell you why. Fine, like okay, it's going to be the main scale, main, and this is going to be the what's the next scale? Vernier scale, vernier scale. Okay, I just write this a little bit faster to catch up. So it's going to be vernier scale. Understand? Now that's perfect. Main scale and vernier scale. So now tell me, people, which scale is vertically calibrated? Vernier, main scale. Look at the board. That's going to be main scale. Main scale is vertically calibrated. Okay. So which scale is horizontally calibrated? We keep the micrometer screw gauge like this. Which part? The vernier scales. Okay. Understand? Doubts until now? No doubts. Fine. Right. Okay. So I'm going to erase this. Now tell me, people, what did I say this green color part? Not this main scale, green color part. I said that. Why did I color it in green? I have put here an arrow. Wait, it's going to move in this horizontal axis. Then I color this main scale in the color part. That means it's going to move with this green color. Understand? Okay, fine. Now the main scale is okay. You have a little bit idea how the main scale will move. Main scale. Now let's go into the vernier scale. Vernier scale, I colored it in blue color. Okay, you can see the colors, right? Uh, who? Guy, online guy. Can you see the difference between green and blue color? Green. Just let me know. If not, you can see, they can't see that. Online people. Yes. Okay. You can distinguish these two colors, ne? Green and blue. Yes. Okay. So now this blue color, I said this light blue is going to be what? It's going to rotate. Rotate. Then tell me now this vernier scale. If I colored it in blue color, that's going to rotate. So the main scale is going to move horizontally and the vernier scale is going to rotate. Okay, this is where the which principle? Now we are talking about scale, so we are talking about vernier or screw. Vernier, which principle? Circular vernier principle. We are taking the readings by circular vernier principles. Right, fine by now. Now we know an idea about vernier scale. It's going to rotate. So this is going to rotate. While rotating, since this part is going to be, I say this is going to only rotate, but while rotating, whole part is going to move along this. Understand? While this is going to rotate, this is going to move. Yes, like that. Okay, this is going to move like this. Fine. Right. Now the next part is how to take a reading. Okay, how to take a reading. So I say that this is going to use the what principle? Mechanically, this is going to use the screw principle. So last time I said that how to take the least count of a screw principle. How? Method to take least count from a screw principle instrument. Right. So let's recall the last class. Least count, count. Okay. So I said something called pitch. What? Pitch. What's it? Pitch. It's a playground. Call a pitch. The playground. So this pitch means, meaning of this pitch, the distance, let's call it distance for now. Distance moved by the screw when it is rotate by how many degrees? By how many degrees? 360. One rotation has how many degrees? 300 degrees. So when you rotate this screw 360, this screw is going to move how many? This amount of millimeters. Small scale is going to be millimeters. So pitch means the distance that's going to be traveled when you are going to turn it one row. Fine. So this pitch you are going to divide by. So normally when you are taking the short method to take least count of a vernier caliper. A vernier caliper is how? Recall it. Smallest division, length of smallest division of the main scale divided by the number of vernier divisions, vernier scale divisions. Okay, so here you are going to come length is a length of smallest between two. So if I have to write it briefly, it's going to be like this: length between two smallest main scale length to main scale division. Okay, you have big main scale division and small main scale division. To be more specific, I can write it like this. Sorry. Length between two small main scale. Okay, this small part, people, not that much important. Okay, normally, generally, you write it length between two main scale divisions. They are going to mean it as the small. Okay, so if you want to write it small, that's also okay. Okay, fine. So I wrote it much specifically here. You are going to divide this by. You are going to divide this by. Y also came. Fine. You are going to divide this by number of vernier scale. Okay, fine. So here the micrometer screw gauge numerator was pitch because it is screw principle. But here it's going to be the same number of vernier scale divisions. So number of vernier scale divisions, but here micrometer screw gauge, that's the rotating or circular vernier scale. So here specific, so that it's going to be number of division in the cylindrical scale or the circular scale, number of divisions in the. So I'm going to erase this part. If you want, you can again write in a notebook, or when we are going into lectures, when you're going to university, they are not going to mention this, write this separately or write this. They are not giving time. They just do the lecture. If we have any important points, we're going to take a note. Okay, so if you want to do like that, I have given everything in the tute and I'm giving you time to write. But if there are something that I'm going to write on the board and not telling you all to write it, if you want, you can write it. Okay, like a note, important points. So to revise, you can write that again. Okay, fine. So here what I'm going to I'm going to erase this part because I don't need it now. Now number of circular vernier scale okay, fine, right. Now this is how we calculate the fine, right. Now let's go to the tute. So I said that these are the parts. Okay, now there's something that is really important, not to the readings or not to not to move this and not to use this gadget. It's for the safety of the gadget, safety of this instrument. Okay, safety in the sense we should use that. Safety in the sense I now you are in a rush, you're going to take a reading. So in a rush you can't think about safeties, you are going to take a risk. Okay, like that, if you're thinking like that, if you're going to take the reading is going to be get wrong. There's going to be an error. So it's for the safety of the instrument as well as to the accuracy of the measurement. Okay, this part I'll draw it in a red color. Let's use a magenta color. It's going to be here. Okay, online people and physical people, can you see this? Online people can see this separately. Can you see this part? So this is also going to rotate, but these two are separate. We can rotate this blue color while we are rotating. This pink color is going to also rotate. It is fixed to this. But when we are rotating this part, blue color is not going to rotate. Blue color is going to rotate slowly than this rotational speed of this pink color. Okay, just don't put like this is that much complex, this is that much simple. These two are going to get rotated. When you are rotating this main part, this pink color is also going rotated with the same speed, same rotational speed. But when you are going to turn this color part, the speed of these two is different. This is going to turn with the speed of our hand. This blue color is going to do slowly. Understand? So this part is known as, well, no, if you have used microscope and if you can remember the parts of a microscope, you have two adjustments: coarse adjustment and fine adjustments. What's the difference between coarse adjustment and fine adjustment? Coarse in the sense, yeah, you have to focus it much soonly. You're going to use the coarse adjustment, but still you using the coarse adjustment is going to differentiate soon. A large, the lens is going to come, going to go a huge, a long distance. Going to go from here to like, long distance is going to be centimeters. Right? Centimeters. Right? For one rotary is going to be centimeters. So the next fine adjustment is in, okay. Now I'm almost near to focus the slide in the microscope, but not accurately focused. So what I'm going to do now is I'm going to use fine adjustment. Now the fine adjustment, people, the lens is going to move 1 millimeters per rotation. The coarse adjustment, the lens is moving 1 centimeter per rotation. In fine adjustment, it's going to move a little bit slowly. Now we can focus it clearly. Understand? So likewise, in this instrument, this is the coarse adjustment. So this is not the name of this part. I'm just going to give you a brief idea. So this is the coarse adjustment, and this is the fine adjustment. Okay, I'll cut it down here. Okay, this is coarse adjustment, this is fine adjustment. Okay, now pay your attention, look clearly. Okay, so now I know the parts, these are the parts, and I'll tell what's the name of these parts specifically in this micrometer screw gauge. So they have different sort of like uh, weird names, but you can remember them. So I'll come to that part. Before that, I have to do a main tell you a main thing. You have to know this importantly. The thing is, I'm going to take a reading. Now we have, you know, the labels, you know, the names of these parts, the purpose of these parts. Now we are going to take a reading. Okay, now this is a separate division. Now think that I am going to take this, the diameter of this ball. I'm going to take the diameter of this. Okay, remember that when you are going to take a reading, this is the first step. We took the least count, we checked if there's a zero error. There can be zero errors. All the stuff finished. Now we are going to take this reading. Now I turn this and I'm going to take the reading. I'm turning this way to move this in which direction? I'm moving this in clockwise to go direction to catch the ball. Okay, I'm catching the ball by hand and I'm turning, I'm rotating this to the ball. Fine. But you have to remember, you are not going to touch the ball by this part. Now I say that this green color is a fixed part, right? This green color is part that's going to move. Now when the ball is here, okay, I'll draw it. So this is the ball. Okay, touch this ball with the fixed part. I'll name it as F. This is the moving part. Now I'm not going to take this much closer to this part. I'm going to keep a little bit gap. Why? Because people, if this is a steel ball, let's think this is the aluminium ball, not steel, then aluminium ball. So which is harder, aluminium or steel? The hardness of steel larger than the hardness of an aluminium. Aluminium is going to it's to deform. You take a knife and cut aluminium something, it's going to get scratched. Okay, it's easy to get scratched. Now this ball is aluminium, but these jaws are so the jaws are harder than this ball. Okay, if you watch closely, I move this, and if I touch this ball, I don't know in the micro scale, I don't know if exactly touched or not. So still somebody who is careless, who don't know the instructions to this practical, this he can't feel the ball. So mostly after experience only you can know that this is the ball. You're going to turn this way, you're going to feel it. You're going to feel that it's not going to move further. So until if somebody doesn't knows that, you're going to turn it again and again. Turn it again and again. So when you're turning this clockwise, and if you don't feel that this this moving part is touching this ball, what's going to happen? Diameter of this ball is going to, or this is going to get worn out. So what happened? This aluminium is going to get the diameter is, if the diameter is 5 centimeters, the actual diameter, you are going to get 4.9. Okay, that's an okay. So to avoid this error, we are going to do something. And not only that, aluminium is the steel object is, or steel harder than aluminium. hard. Compare the hardness, steel hard. So until now, I said that aluminum is going to get deformed. But now I'm saying that aluminum is going to deform, but steel is also going to get deformed. But if you take the percentage, aluminum is going to burn out a higher percentage, steel is going to get burn out a little bit. So, okay, fine. One boy came here, he did instructions, turned this screw, and he crushed the bone, this part. Okay, this here. Okay, fine. That sphere is small sphere, aluminum wall, that's going to be 2 rupees. Okay, it's okay, I can take and I can measure it. But people, if you scratch this part, if this moving part is going to get deformed or worn out, what happens? Can you remember in the vernier caliper, I said that the reasons for zero errors, okay, positive and negative zero error. I said one of the reason to negative zero error is this door getting wasted or worn out. Okay, negative zero. So likewise, this part gets worn out, there is going to be error until error when we are every time when we are using this micrometer screw gauge. Okay, so that's not going to get corrected again. Okay, fine, it's a zero error, we can correct it, but that's what, that's not good enough. Like if there's a zero error, we have to calculate, we have to spend time to do a calculation. So to this purpose, what we do is we use this inbuilt part, this fine adjustment part. Understand? Okay. Before going to that, I have to come to again to the measurements part. Now we went inside the practical. We are going to come again outside of the practical. Outside in the sense, we are going to look into some theory. Fine. So we recall the vernier caliper stuffs. It's going to be like this. It's going to be like this. I said that the distance between I said that the distance between these two jaws, the distance between jaws, distance between reading. This vernier caliper doesn't have a zero error. The distance, I said three things are equal. What? Let me recall again. Distance, uh, you can note it down. This is a little bit important. Distance between two jaws, yes, no any zero error. I'll write it in white color. If no zero error, I wrote it in short form. If there's no any zero error, you can write in long form. There's no any zero error. Distance between two jaws is going to be equal to the distance between the zero of the two scales. What's the meaning of this? I said that the distance between this equal to the distance between, if there's the zero of the main scale and the zero of the vernier scale, this distance. Which distance? This distance is equal to this distance. If there's no any no error. Understand? Okay, fine. So between zeros is equal to between zeros. And the next part I said, okay, fine. For now, let's go into micrometer. So this is again equal to what? Distance between two jaws, distance between the two zeros, and the next part, what's it? Distance, sorry. of measurement. So we have to equalize this. Okay. What? Distance between two jaws. Okay, that's equal to the distance between two zeros of the two side scales, and this should be equal to the reading of the measurement. Reading of the measurement. Reading of reading, not of reading from the measurement. From the reading from the measurement in the sense, if we are going to take a diameter, it's going to be diameter. We are going to take the length of a ruler, length of a cuboidal shape. That's going to be the length of the cuboidal shape, the correct length. This is going to be equal to the distance between two scales and the distance. Okay, so likewise in applicable to the vernier caliper. Okay, we know that. And now I'm saying that since we are in the micrometer screw gauge, this is also applicable to the micrometer screw. So the distance between not series blue. Okay, fine. So the distance between this equal to the distance between this and the distance between diameter. Diameter equal to the distance between those and the distance between the two. But since there's a small tiny difference, you want, you can mention in this part, this is applicable to vernier caliper, but the difference is white color. This is an important part. The difference is this thing. That's it. Distance between the zeros of the two scale, zeros of the two scales is not going to get related to micrometer screw. Why? Because the vernier scale is circular scale. It's a circular scale. Since it's rotating like a horizontal vertical direction compared to the direction of this main scale, so you take distance of this 0 and this 0, it's going to be a distance like this. Okay, understand? It's going to be a distance like this. So this is hardly applicable. This is applicable with conditions that's not needed to A-level syllabus. But if you take the distance, it's going to be a distance like this, because the zero error is going to move like this in another direction. I said that before, I mentioned it. But in vernier scale, you are moving horizontally in one plane. So the direction, the distance between the two zeros of the two scale is equal. The reading. Understand? So you have to mention this is going to be, note it down if you want. In the tute itself, you can take a small space and you can write the important points. This is going to be in micrometer. I'll write it as a short form. Micrometer screw gauge. In micrometer screw gauge, distance was of distance between rows of two scales, not but linear, not linear. The additional part of this is an additional part. Okay, you are not going to be questioned from this theory. This is an additional part. You have to remember. Fine, not going to be linear. Right. So now I said the distance between these rows is equal to the distance between this to the diameter, the reading. Okay. So find by now. So if this moving jaw or if this fixed jaw is going to get worn out or going to get damaged, what happens? The distance between these two jaws is going to get differentiated. So a small part is going to add, a small part is going to get reduced. So if that happens, distance between not going to be same as the distance between those. Understand? Okay. So from that, by when it happens, if this is going to worn out or if this is going to get corroded, that's going to be an error. So those type of error is known as zero errors. Fine. Right. Okay. Complete the theory part. Right. we know how to calculate the least count. Okay, we know how to calculate the least count. I said every how this is moving, and I said the purpose of this part, and the only part is how to take a reading. Okay, to take a reading, let's do some exercise and see how you can get practice use. Fine. Now let's go write the note. So this is not the fine adjustment. So I have given you the parts. So did I say to bring you the theory tube? 1/4. Not 1/4, the practical tube. Did you bring it? Bring it. You? Practical tube? Brown color tube? Brown color? No, practical tube? Color, no? Pink color? You? So take your practical tube. Take your practical tube. Go to page number 21. 21. Have a micrometer screw gauge. Okay? Micrometer screw gauge. Now, what we are going to do? We are going to label this. We are going to label this instrument. Okay. Fine. So this fixed jaw, let's use color. Important. Not important now. Right. This is fine. So let's use the yellow color. This weird, this fixed jaw has a weird name and known as, this is a fixed jaw. We don't call it as a fixed jaw. This is as anvil. 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 Okay, right. Jaw is known as anvil. It's a weird name. Have you heard this name before? You know Alvin. You know Alvin, but this is anvil. So since this is anvil, is this chipmunk? What's this? This is going to be this spindle. Okay, spindle is going to be known as the spindle. So the spindle is the moving guy part. Fine. So this rotating course adjustment, I say this is like a course adjustment. This is known as the thimble. Don't think these are the names from different languages. That is given for mechanical engineering parts. Okay, thimble. And this fine adjustment part is going to be as racket. You know racket, badminton racket. Not racket, is ratchet. Ratchet. We call it ratchet. Now silently, ratchet. Yes. Character. Sorry, a role in Guardians of the Galaxy. Ratchet. No, rocket or something. Something like this. Guardians of the Galaxy. There's a guy, a raccoon. Maybe something sort of like this. I can't remember. Can online people remember that name? Fine. Okay. Now we have only one completed anvil, spindle, ratchet, and thimble. So we have only two parts. Meaning these parts are, these are not weird, guys. Very simple. Okay. This horseshoe magnet sort of thingy is known as the frame. Frame. You all know frame, right? Frame. Right. And this part, this main scale part, part is as the sleeve. Sleeve in the sense, not exactly the main scale, whole part. Whole part. Just I have put that arrow here. I have not mentioned this main scale, okay? I have this common part known as the sleeve. Do you know what a sleeve? A shirt, you have a sleeve, right? Like sort of things. I think that's because this is round and some sort of thingy. They have named it as sleeve. Okay, you know this. You have heard sleeve. You have heard frame. Oh, who have heard anvil, spindle, ratchet, and thimble? I haven't heard when I was doing this. After this, I have heard many times. Okay, why online people? You're not responding. Can't remember name of that guy. Rocket, rocket. Have heard of, but not. Yeah, heard of anvil. Yes, heard about the anvil, not the measuring instrument. Okay, fine. So spindle, ratchet, sleeve, and the next part. Okay, so 1, 2, and 4. So next, we are not going to label it. We are going to mention some parts. I think. Can you show? Have two. That's main scale. So now I'll use dark blue, purple, purple. This part and this part is going to be the general name, the main scale, and this is going to be the not vernier scale. This is rotating vernier scale. Okay, rotating vernier scale. Rotating vernier scale. Fine. Okay. So I have given the same exact picture in this micrometer screw gauge tube. Now finished, you completed this practical tube. Go to micrometer tube. So you have a space to write about the least count. So least count of. So can you remember the definition for least count for vernier caliper? As the least count of vernier caliper. I say generally you have a definition for least count. So least count is going to be the minimum measurement that you can take from an instrument. That's the general definition. For a vernier caliper, that's it. The distance moved by the moving jaw when is going from when the vernier scale is going to coincide the first division of the main scale. Yes, no, any okay. Understand? That's the distance between two jaws when the moving scale is going to when the vernier scale is going to coincide with the main scale's first division. Okay, that distance between two can be the least count. So we are going to write the least count of this micrometer screw gauge. Okay, when you're writing this, you have to be really alert. Okay, you have to focus on the sentence that I'm saying. Okay, fine. Right, start right. First, before that, we have to a little explain about the pitch, and after that, we have to explain about least count. Okay, the distance traveled by the distance traveled by the the distance traveled by the edge of the circular scale, edge of the circular scale, edge of the circular scale along the main scale, traveled by the edge of the circular scale along the main scale, comma, when the zeroth division, when the zeroth division of the circular scale, moves. Now we are rotating this in the which direction? Clockwise direction, anti-clockwise direction. We are going to take a distance, we are going to turn it clockwise. Anti-clockwise in the sense there's a 0 here. So the 0 here is going to move downward. Okay. I said that 0th division. Not 0th division, so 0th division. First division. When the first division, of the circular scale, first division of the circular scale, I said moves, right? Did I say move? Circular scale, cut that move and write circular scale. And the first division of the circular scale coincides the line of main scale. The line of the main scale. Line of the main scale. And the first division of the circular scale coincides with the line of the main scale. The distance traveled by the edge of the circular scale along the main scale when the first division of the circular scale coincides with the line of the main scale. Understand? Okay. So that's going to be the least count. Least count in the sense the distance traveled by this this d. Okay. This d is the distance. So that distance is going to be least count when the 0th scale, here is the 0th scale. Okay, fine. White color, I think. How is it? Maybe like this. Fine, whatever. So now you can see this, the whole thing. So here was the random access tree of this. So to random things doesn't give access. Here not clear, ne? Color can be used. Dark color. Blue. Brightness of my good. You can't see the board clearly. Can you? Online people? Hard. You can put a filter. Going to get inverted. Let me try. Black and white. Black and white. Fine, fine. What can we do? I think we have to go to another but they are going to get blind by the brightness. Okay, fine, fine, fine. So here see, I'm going to draw it again. I'll use white color. So this is the rotating scales vernier, rotating parts vernier scale, and this is the main scale. So what I said is, here's the 0, and this finishes here. And if I go to this part, you have some divisions here. And 0 is going to be here. Okay, just look this only this pink color part. Forget about this part. Okay, forget about the 0 part because this is not that much accurate. I did it just for to explain this, explain the discount. So fine, this is the 0. There's no any 0 error. Okay, I'll do the other parts. I'll use green color. So this is going to be dotted lines, and this is the moving part, and this is the anvil, and this is the spindle. This is anvil, and this is the spindle. Okay, anvil and spindle. Just remember that name: anvil, spindle, anvil, spindle. Then you will get familiar to this. Okay, I drew dotted lines because I can't draw the whole picture. Fine. So when these two are coinciding and there's no 0, let's assume there's no any 0 error. When these two are coinciding, the 0 of the vernier scale, the circular scale, is going to be coincided with, you can see a line here, ne? The main line of the principal, main line of the main scale, principal line of the main scale. Okay, this 0th division and the principal line of the main scale is going to get coincided. Coincidence is going to get aligned. That means that's this distance. That's this distance. In the sense, there's no any distance. The distance is 0, so the reading is 0. I said to look only this pink color part. Okay, now I'll say why I didn't tell you to look in white color part. So white color part here, this is 0th division of the what? The main scale. So normally practical, just go to page number, the image, go to page number 1. I have given you questions in the practical micrometer gauge tube. Go to page, not that page number 1. You have questions. I have given you separate pages. After the topic of question, our page of questions, you have the first page of the question is the questions from of the micrometer screw. Go to the first picture. This is the question part of the micrometer screw gauge tube. Go to this page and you have a picture. You have many pictures. Look this picture. Okay, look into this picture. Can you see a 0 division there? The main scale. Okay, fine. So go to this picture. Here you can see that. Second picture, Roman number 2. Okay, in this picture you can see a 0 scale, and can you see a 0 scale in this rotating scale? Okay, 0 scale. Now here what has happened is this 0 have not aligned with the main scale's 0. It is moved a little bit like this. Okay, so if it is moved, there's going to be, okay, and you can see there is some there are some divisions here in the main scale also, some division scale also, right? So when this 0 is aligned with the main scale's principal axis, the next thing that's going to happen is, let's erase these parts. Okay, what's going to happen is the main scale, this part is going to, here the 0th of the main scale should align. I'll mark it in super clear. No, that's not good. Paste this, take magenta, line here. This is the 0th of the main scale. Okay, now what I'm going to do is I'm going to select this all, and here when there's no distance these two jaws, this magenta color is going to be the starting point of this rotating scale. Understand? So you can see that I'll use color. This this line, this white color line, that white color line and the magenta color line is get aligned. There's no any distance. Not only that, zeroth of the vernier scale is going to be lined up with the principal axis, but we can't see the principal axis now. Why? The principal axis is after the 0. So after the 0, in this picture, but I say this picture is not accurate, it's because I have lined the principal line only up to this. Look into the picture in this book. They have produced this line. Produce, you'll know the meaning of the produce, right? From all else. Produce like this. It's not finishing here, it's moving here. Why? Why? See if there's any zero error. So now then you take this part here, and if it is aligned with the 0 of the vernier scale, we can see principal line of the main scale. It is coincided with the vernier scale 0 division. So if it's not coincided, this will be like here or here. I mean, this part is not moving, could be here, but this pink color part would be somewhere else. Okay, so for that reference only, they have produced this part, but reduced the main scale part. Okay, so when there's no any zero error, the picture is going to be like this. Like what? Like this. You're going to have a picture like this. You can't see this 0. Which 0? This 0 is hidden. Sometimes, no, that 0 is hidden in the sense, it's a part of that 0 is going to be like this. Part of 0. Half of that 0. They have written that 0 in this line. Align it, that 0 center to this line. You can see half of that 0. Okay, so that's different from one instrument to another instrument, from 1 micrometer screw gauge to 1 micrometer screw gauge. If the brand is planning to put that 0 somewhere else, that's going to be different. Okay, so now generally you can see only a part of this 0. Okay, and this line is also going to be invisible. Which line? This part, white color part. White color part is going to be visible, and the 0th part. Okay, fine. Okay, this is the initial reading. Initial reading in the sense, if there's no any 0 error. Understand? Fine. Now when we start to rotate this, the clockwise direction, there's going to be a gap here. That's how we start take a reading. Now we rotate and rotate and rotate and rotate. We are not going to take it off from the gauge at all. We are going to rotate for a distance that is greater than the reading that we are going to take. If there's a sphere and if this distance is 5 centimeters, we are going to move this something larger than this. The spindle is here and the anvil is here. Anvil is here. So we have to keep a gap, big gap, larger than the ball. Understand? Right. So that's how we start to take reading. First of all, initially we should know the least count. We should check whether there's any 0 error. After that, we are going to move this away and we are going to keep the ball. And next step is very sad because this is not going to can minimize. Take the pen. And we read. Fine. Now what I am going to tell you all is, when we are moving this gear, this is going to come out and we keep the ball touching the fixed jaw. We are going to keep the ball with this fixed jaw. So that's the ball. We are going to keep this here touching the fixed jaw and we are going to move this away. And now what we are going to do is, this pink color anvil is here. Now the yellow color ball that's touching here, I'll draw a light this ball. I'll just I crunch this. So since there are a lot of editings here, it's stuck. Fine. And the fixed jaw is going to be here. Okay. Now what I'm going to do is I'm going to rotate this clockwise, and little by little I'm going to move this by touching the thimble. Which part? Thimble. By touching the thimble, I'm going to rotate this. That's the course adjustment. Now little by little I'm coming here. So now I'm here. Okay. And again I'm coming here. Is the first, is the second. Okay. But keep in mind, I am not going to touch this. I'm going here to this sphere, but I'm going to not touch this. Okay, fine. After that, what I'm going to do, this picture, I can't zoom it. So you have a part known as ratchet, and that's the fine adjustment part. Okay, fine adjustment part. Just think like that. Now what I'm going to do is I'm going to take my fingers off from the thimble. I'm going to touch the ratchet. Okay, the ratchet, when you're turning the ratchet, is a bit satisfying. Okay, you can hear something, I'll tell you. So now what you are going to do is you're going to turn this ratchet. Okay, now the ratchet turning faster than the thimble. Okay, now this ratchet is moving. Now if we think mechanically from here to here, let's take the distance is d. It took 5 seconds. So not 5 seconds. Let's take 1 second. 1 second. Then we are rotating the which part? Thimble. Okay, the thing to come to not this. Give some let's substitute some values, then you'll understand better. So when you're using the thimble, okay, thimble, it when you for 1 second, when you're rotating with the same speed, for 1 second it went 5 centimeters. Okay, again if you're again when you're touching the which part, the ratchet, when you are going to turn it with the same speed, it's going to move 1 centimeter take a centimeter per 1 second. Understand? Because this is the fine region, it's going to move by little. Understand? Right, that's what I have to explain you all. So now I am turning the thimble. They have made that thimble that much smoother, because when we are turning this, now this is coming little by little. Okay, little by little. So I'll erase these pieces. Okay, now this is coming here by little. Okay, here, and now it's going to touch the surface. Going to touch the surface. Touch the surface only when we are rotating the ratchet. So they have made this instrument that if this touches the surface, which is harder than a rubber or harder than a sponge, then going to stop automatically. But now, if we didn't stop rotating the ratchet, you think this is going to move here, going to crush the ball? No, that's not going to happen. At the first moment this touches the sphere, we forget to stop rotating this ratchet, this is not going to move, because this knows that this has caught the ball. Okay, one day I'll bring a micrometer plate. It's not like a magic thing. They have made a small spring inside this ratchet. Okay, so when it touches the ball, okay, this spring gets the spring is going to get compressed, because it can't move further. So that part, a lock inside there, is going to get off, and only the ratchet is going to move, but not this moving jaw is going to move. So when you reach this point, now you are turning and turning, but you don't know. The ratchet knows I have caught the ball, but you don't know. For that, to remind you that you have caught the ball, when you are going to touch the surface and when you are going to rotate, you are going to hear a tick sound. So you are using a manual gear vehicle, if you have gone to petrol sheds, they have a lid to the petrol to put the fuel. So once you close the fuel fully, there are some sort of this mechanical concept is applied to some water bottles also. So once you have closed fully, and if you take some water bottles, you tight it up, and if you give to your father, he's going to tight it up that much, so you can't turn it around again. So in some bottles, if you are going to tight it over a limit, that lid is going to get broken. Okay, so understand, to save to protect those lids in those mechanical instruments, like not mechanical instrument, in vehicles, they have attached this mechanism. If it is completely rotated, and if we keep rotating, it's not going to move, but you are going to hear a tick 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 sound. You're going to hear tick tick sound. That means the part you are turning is only rotating, but that lid is not going to move. Okay, that's a small sort of mechanical. I'll show a video here. Not today. I didn't get prepared to show that video. I'll show it later. So when this touches, you are going to hear a ticky. So here in the book, they have mentioned ticky ticky sound, not a ticky ticky sound. It's going to be tick tick sound, like a satisfying sound, like this, not like double sounded. Less when you are rotating, it's going to be heard frequently. Okay, fine. So when you are going to hear the tick tick sound, what are you going to do? You are going to stop rotating. Now what you are going to do? You are going to take the. So now we are going to take the reading. So this is how you take a reading. So let's go to the note. No, before going to note, I'll tell you how to take a reading. So this is how we are going to take the reading. Let's go to any page, a little bit focused, then we can do some questions. So this is how we take a reading. The main scale is here. Pay attention. Oh, do you need a break? Tough. 9:46. I'll give the break at 10. So we have another 15 minutes. Let's focus. So this is the zero scale, and this is the vernier part, the main scale part, and this is the vernier scale part. Now let's think that the zero is not here. You can't see the zero. The zero is somewhere else. So this is how you take a reading. You have like this, like this, like this divisions, like this, like this division. Sorry, have like this and like this division. Fine. So here there are like these sort of micrometers, and there are micrometers you have zero, and you don't have these downward parts. Okay, so normally, generally, it's going to be like this. It's going to be like this. It's going to be a sort of extended vernier scale. And remember, it's a special case. Likewise, this is going to be like this, but not like in extended vernier scales. In the next part of the micrometer scale, it's easier, much easier than this. Take the reading. Okay, fine. Now, what they are saying in the instruments manual is they are saying that the distance between this zero, they have mentioned zero, and they are mentioning here 1 centimeter. If it's 1 centimeter, they are going to mention 1 centimeter. So the distance between this is going to be 1 millimeter. So they are going to put this part. Yes. So this distance is going to be how much? The half of 1 millimeter is going to be 0.5 millimeter. So what is the smallest, the length of smallest division of the main scale? That's going to be 0.5. So again, you can find the least count in this way also. 0.5 millimeters divided by number of vernier scale, number of circular scale. I'm a guy who is going to slip. Fine. So understand, you can take the least count like this also. So I'll remind it again when we're doing some question. There are questions in that way also. So this is going to be 0.5. So this is how we take the reading. So how we took the reading from a vernier scale? We are going to look the main scale division, which is in front of the zeroth of the vernier scale. Zeroth of the vernier scale. Okay. Now what I'm going to do is I'm going to take. That's all. Now we are going to do this part. I'm going to look the division that is in front of the vernier scale. This division. Sorry. I have to put this. I'm going to see what is this. So this is 1 millimeter, this is 2 millimeter, this is 3 millimeter, this is 4 millimeter. So the reading is 4 millimeter, is it? No, I have to add something. This is 4 millimeter. 4 millimeter. Now what we are going to do is I'm going to add something. That's the number of vernier scale division that is coincided with the main. Okay. Now this main scale's principal line is, let's assume that it is coincided with the 45th vernier scale, 45th circular vernier scale. So we are going to read this. So if this is not the 45th, we are going to count it. So you are going to have 45 here and 40. Let's tell this is 40, 45, 46, 40, 48, 48. These are mentioned in the micrometer screw gauge. The in between lines are, they haven't marked the number. So we are going to count 40. If this is 45, this is 40, this is going to be 46. We have to count one by one. So what is the number? What's the number of this vernier scale? It's going to be 46. Okay. So what we did in vernier caliper, we wrote this 46 and multiplied by the least count. So I'm going to multiply this by the least count of this vernier scale. Okay. So let's assume that the least count is going to be white color. 0.01. 0.0. So we divided this by 0.01 milli. This 46 doesn't have a unit, but this 0.1 has a unit. So you multiply by this, this part is going to have a unit. So this part is going to have a unit separately. You add up, a 3D. So the part here is, this is going to be 4 millimeters. You are going to have 0.46 millimeters. And finally, you are going to have, the reading is going to be 4.46 millimeters. So in a vernier caliper, you took the reading until this decimal place. In a micrometer screw gauge, you are going to take until another decimal place. So which instrument has a high accuracy? Micrometer screw. Okay, fine. This is how you take a reading. Now let's go to the tute and complete it. So we finished what a least count is. Fine, right? So go to page number 1, starting page. So you have a box to fill the least count of the instrument. This is how we calculate the least count of the instrument. Least count of the instrument. Least count of the instrument. That is going to be the pitch divided by the number of divisions, number of circular vernier scale division. But you write like this: number of circular vernier scale, number of circular vernier scale divisions. Right in that box. Least count of the instrument. Pitch divided by the number of circular vernier scale divisions. Circular vernier scale divisions. Fine. So after that, you have a small box L.C. That's the short form. In short form, you write as LC. LC is going to be equals to over N. Over N. So here, put a bracket, write it as P. Here, put a bracket, write it as N. Okay, over N. So you have an example. Main scale of a micrometer is marked in 1 millimeter divisions. Main scale is marked as 1 millimeter divisions. The pitch of this instrument is 0.5. Number of divisions in the cylindrical scale is 50. Find the least count of the instrument. So the least count of the instrument is going to be, what's the pitch? It's going to be 0.5 millimeters. And we are going to divide this by the number of circular scale divisions. That's going to be 50. So this is going to be, how we are going to calculate this? 5 people? Here divide by 5, 10. Here divide by 5, 0.1. 0.1 divided by 10, you are going to go one decimal place. It can be 0.01 millimeter. Okay. So generally, this is the least count of the micrometer screw gauge most of the time. So what's the least count of the vernier caliper? Most will be 0.1 millimeter. So in micrometer screw gauge, 0.01. So mostly you have to remember this 0.5 divided by 50. Most of the time it's going to be the least count. Fine. So the next page you have how to obtain a reading. So let's read it. Let's have a read on it. Go to the next page. Okay. Obtaining the reading, when the thimble is turned clockwise, the spindle moves towards the anvil. Okay, highlight thimble, highlight this part. Thimble turned clockwise, spindle moves towards the anvil. Thimble clockwise, spindle, not spindle, spindle towards, only towards. You can highlight this part. Highlight the sentence if you're not good like me. Thimble is the turned clockwise, the spindle moves towards the anvil. So clockwise and towards. That's the most important part, clockwise and towards. The next point, when the thimble is turned anti-clockwise, spindle moves away from the anvil. So highlight anti-clockwise and away. Okay, right. Then the next point, when the spindle and anvil are in contact, if there is no zero error, the zero division in the cylindrical scale, okay, cylindrical scale in the sense circular scale, coincides with the zero division of the main scale, zeroth division of the main scale. Okay, so here, fine. Division of the main in the main scale. When an object is placed between coincide the zero of the main scale, you know that point. Okay, I explained you. So the fourth point, when an object is placed between anvil and spindle, the edge of the cylindrical scale moves away from the zero division of the main scale. Okay, when you place an object, the edge of the cylindrical scale, what's the edge of the cylindrical scale? This is the edge. This part is the edge of the cylindrical scale. Okay, that moves away from the zeroth of the main scale. Find the distance between the distance between spindle and anvil is equal to the distance between zero division of the main scale and the edge of the cylinder. Okay, the zeroth of the main scale and the edge of the cylinder. Right. Now we have a point. This distance, okay, I said that you have to measure like something like this, but not like that. This distance, this edge of the cylindrical scale and the starting point of the zero scale, this distance is going to be the equal to the distance between this. Okay, so here you have to change something. What's it? Here in micrometer screw gauge, the distance between zeros of the two scale is not linear. Two scale is not linear, but here you are not taking the distance between two zeros. You are going to take the distance between the zeroth of the main scale and the edge of the cylindrical scale. So you can write again here. You can write it again. That sentence. You have copied this down in your notebook. Write this sentence here. Which sentence? Sentence is this: not. Distance between the spindle and anvil is equal to the distance between zeroth division of the main scale and edge of the cylinder. Distance between zeroth of the main scale and the edge of the cylindrical scale. Fine. That's about the micrometer screw. Then the next point is the object whose measurement is to be obtained should be placed between spindle and anvil. Okay, spindle and anvil. Ratchet should be turned until a ticky sound is heard. Not ticky ticky, it's tick tick. Yeah, so honk. I will heard that. Right. Okay. Ticky sound is heard. I let that ticky ticky part. So you can write ticky or tick tick, whatever. You are going to write click click, that's also fine. Just write the known as onomatopoeia. Okay, then the next point, then the main scale division just before the edge of the cylindrical scale should be recorded. Okay, but the main scale division just before the vernier scale should be recorded. This part, this scale just before the cylindrical scale, edge of the cylindrical scale should be recorded, and take it as x, take it as x, take it as x. If the line of coincidence, now we took it as x millimeters, x, we took it as x millimeters. If the line of coincidence in the cylindrical scale, if the line of coincidence in the cylindrical scale with the datum line is n millimeters, so here you don't use this in source book, so I say this is the principal axis. So in higher studies, you call this sort of stuff like principal axis stuff, call it as a datum, like a reference point. The meaning of datum is reference point. Okay, so datum. So that's what they are saying. If the line of coincidence in the cylindrical scale with the datum line is n, the line of coincidence is n, and the least count of the instrument is y, so it's going to be n multiplied by y. Okay, you're going to add the main scale reading just before the edge of the cylindrical scale, the coincident line in the vernier scale with the datum line multiplied by the least count of the instrument. Okay, so this is going to be in millimeters. Okay, write it down in the reading part. You have two boxes. In the small box, you have reading is equals to x plus ny millimeters. X plus ny millimeters. Okay, so we can go have a break. Okay, right. So you have to write this descriptively. The next huge box, reading is equal to x. This x you are going to write reading of the main scale, 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 plus number of divisions coincide, divisions, number of divisions coincide in cylindrical scale, cylindrical scale, cylindrical scale. Number of divisions coincide in the cylindrical scale, and you have to multiply this part by multiply this part by least count. Reading of the main scale, reading of the main scale, of the main scale, number of division coincided in the cylindrical scale, number of divisions coincided in the cylindrical scale, number of divisions coincided cylindrical scale, cylindrical scale, cylindrical multiplied by the least count. So first you should multiply this part and add that part to this for mass theorem. Okay, fine. Take your break, take your interval. Okay. Online students, can you hear me? Online students? Okay. Yeah. Right. So, okay. So the Vesak is going to be on 30th, ne? Not coming week. 23rd and 24th. That's it. My calendar has been collapsed. 23rd, 24th. These two are the Vesak. So these 2 days are holidays, public holiday. Day and the day after Vesak. Is it? Only one day. I'll refer it to that. We can keep the class, but the thing is, if someone calls the police, we have to stop it. Yeah. So an announcement. So next class, you'll have this next class. Don't worry. So after that, 30th and 31st, you won't be probably. I'll ask that from the institute. So Vesak, you don't have classes. So next month you have 6th and 7th, eh? The holiday. All right. So whole month you're going to have class. Okay. So no holidays. So next week it's going to be really strict. So next month, we are going to start mechanics. But we are going to finish vectors. So those who didn't come to yesterday's class, please watch the recording. Tell your friends. Let them know to. I'll just put a message again. Remind you all. Finish watching the recordings, and after that, like next week, we are going to start traveling microscope. It's really easy. It's a small tute, not this much big. I mean, you have here like almost 6-7 pages. It's going to be like 2-3 pages. Traveling microscope. So traveling microscope plus spherometer. Spherometer just a little more theory. Theory in the sense same principle, same everything is same, but there are some geometrical stuffs there. Okay, so that's a little bit part. So I will give a good knowledge. I won't explain the geometrical parts in spherometer because that's not important to A level. I'll give this and this, this and this. Everything is in a tute. So you can refer the tute and look into spherometers. I will explain how to take readings, but there's a separate geometrical part. I'll show that you all. So next week mostly we are going to cover the other tutes, and we are trying to finish the vectors. Okay, next week. So after the next week, you 31st and 30th and 31st, you won't have the class. I mean, due to the result. So next month we are going to start the mechanics. So after the mechanics, you have to come to the classes every day, because if you are going to miss a class in mechanics, you are going to be in trouble. Okay, fine. So at the last part of this month, Pesuru books are going to get published. So I'll put a Google form. You can fill it. So I'm going to collect the money before I'm going to place the order. So if you will to buy, I'll put every prices. So you have to take a screenshot of the bill payment, and I'll mention the account number. So you have to upload the source document so I can verify it and place your order. Okay. So today or tomorrow I'll put that Google form. If you want Pacer books, it's almost approximately, I think if you're going to take 3 books, the three stuffs, MCQ, essay, and structured essay, it's going to be 6 to 7,000. Okay, because the prices are really high. Printing cost, I think, not me pays the publication, the price had become so much high. So it's going to be that much higher, but that's worth it for that price. That's that much worth it. So I recommend you all to buy those stuff. That's for your personal things. So after I finish some questions from the theory, I'm going to put past paper questions into the tute. I will discuss them. As I'm not going to put all the past paper questions, I will choose some hard questions and put that into tute. I'll explain them, and while I'm explaining, while I'm finishing every unit part by part, you have to do the related MCQ questions from the Facebook books. That's the part that you have to do from your site. Okay, fine. So those are the updates announcement for this month. So after that, let's look into the other things. So recordings, and I'm going to open a new announcement group. So the WhatsApp thing is going to be a little bit different. I'll inform you about those things later. So mostly when you are going to join this online, you are going to be it's a little bit harder. You can't contact with me. There's a lot of obstacles. So I'm going to make some corrections here. So I'm going to open a WhatsApp chat. So when you are doing this in online, you can chat with the other friends, and you can contact with me. You can do whatever stuff. So here in this Google Meets, it's a little bit harder. So I'll tell everything. So it would be fine if you join online also. Okay, so you don't want to come physically. It's not a must, but you should. It's good if you can join those two classes physically, mostly the theory class. Okay, so those are the things that I have to say. Yeah, that's all. So if you have any friends, just tell them what I'm doing, what's good, what's bad. If you have any feedbacks, just tell me, and tell your friends to join the class. Okay, this plan. Okay, so I hope to complete the syllabus within 2 years. Okay, let them know. And it's a risk, but I have made a plan, a full plan, and I'll give a paper if you all want about the plan, how I'm going to complete the syllabuses. So I said you all, while I'm going a little bit mechanics, first unit is measurements, mechanics, then waves and oscillations and heat. Those are the bulky subjects. While I'm finishing these stuffs, I'm going to start other lessons, the part 2 lessons, grade 13 lessons inside this. Okay, while I'm doing these 4 subjects, I'm going to start the other. Then you have only 7 remaining. I'm going to start this 7 in between these stuffs. So you are going to parallelly do waves and oscillations and do fields, electric fields, gravitational fields, all stuff simultaneously. I'll break it down. I'll tell you the plan. So 2 hours I'm going to do something, and other 2 hours I'm going to do the next thing. If not, I will mention you all. Theory class I will do then in order from first to fourth. In the paper class, I'm going to do it in the next order. So one paper class I'm going to teach you all theory, and the next paper class I'm going to give you a paper. Okay, still you're not doing a paper in the paper class. So I have choose this paper class to complete the practical as well as to complete the question tubes. Okay, still I can't make a paper from the knowledge you all have. So it's going to be a little tiny paper. It's really easy. So that's why I'm not issuing a paper. So after we finish the measurements, we're going to have a small paper weekly. Okay, fine. So let's go into some questions in the practical tute. Okay. So first question. Take a tute, micrometer screw gauge tute. Go to page number 1 of the question part. Question. Okay. Fine. What are they saying here? This screw gauge has 0.5 millimeter main scale and circular scale. Has 50 divisions. Calculate the least count and the reading. Calculate the least count and you have to take the reading. Fine. So we are going to take the least count. How to take the least count? Least count is equal to least count is equal to P over N. What's P? Pitch. So the pitch is this screw gauge is 0.5 millimeter main scale. So this is a sort of a little bit different question. So in these questions, most of the time the pitch here is going to be equal to the length of main scales smallest division. So they say that the screw gauge has half millimeter main scales. So that half millimeter is going to be the pitch. If they haven't mentioned the pitch specifically, this is going to be the pitch. Okay, right. So fine. So this is equal to half millimeters. Half in the sense is going to be how many millimeters? In point form, 0.5 millimeters divided by 50 divisions 50. So this is going to be equal to 0.01 millimeters. I said that. Have to do this. You have 0.5 and 50. Okay. I can write this. I'm going this way. 0.5 you can write as 5 over 10. Okay. 50 you can write as 1 over 50. Okay. This to this cancels off. That's going to be 100. This is going to be 10. So this is equal to 1 over 100. So 1 over 100 is equal to 0.01 millimeters. Okay, so these are the steps that you are going to do. Answer a structured question. First, writing the equation is a must. Okay, after that, substitution is a must. You get, if you have three marks to this question, 1 marks is to this substitution, sorry, to the equation, 1 marks to this substitution, and finally you get marks to the value plus the unit. You should have the value with the unit. If you have only the value, 0 marks. Only the unit, 0 marks. If both, that's only you have 1 marks. Okay, so these are the steps. So in between you can have, in between these two you can write as like this. Here I just did it simply. Here I did this simply. You can write this is equal to 5 over 10. Okay, over 1 over 50, right? This to this cancel off 10 here. So this is going to be 1 over 100. They are not going to give marks for this, but you can write. The most important fact is what? Equation, substitution, and final value with the unit. Okay, these are the important steps. Fine. So we found the least count. The least count is 0.01. So we are going to take the reading. The first step, the main scale reading before the edge of the cylindrical scale. That's it. This is 0, 1, 2, 3, and here you have this mark. I said that these marks have the distance of 0.5 with this 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. So let me read this. 1 millimeter, 2 millimeter, this is 3 millimeter. So this distance is 0.5. So this distance is going to be 3.5 millimeters. Understand? Understood? Fine? Right. So the main scale reading just before the edge of the cylindrical scale is reading is equal to 3.5 millimeters plus, what's the coinciding vernier scale? Here you have, let me take a yellow color. Here you have 20, 21 and 22, 23, 24 and 25. So this is the part that's coinciding, right? That's 20. If this is 20, 21, this is 22. So I'm going to write this here. 22. 22. Fine. So I should multiply this by the least count. What's the least count? 0.1 millimeters. 0.01, sorry. 0.01 millimeters. So this is going to be equal to 3.5. Now I'm going to do some calculations. I mean, equation is here. You don't want the equation. This is not an equation, just to take a reading. So I said equations for other subjects. You have PV equal nRT. You have PV equal nRT. You have SC equal UT plus half AT square. Those sort of equations. These are not real equations. They are just remind you all. I gave you all equations. They are not real equations. So substituted. After that, I'm calculating. So when you are calculating, okay, in physics, you need only units for the substitution part. When you're doing calculation, you don't want to write the 3.5. 22 into this is 0.22. So now I'm going to write the final answer. This is going to be 3.72. 3.72. This is the final answer. So I have tried the fine. So this is the reading. Okay, online people. So in the second question, you have following diagrams have main scale half millimeter and 50 divisions in circular scales. Take the reading. Okay. Take the reading of Roman number 1. Second question, Roman number 1. Okay. Online students, text me the reading. Tell me. So when I'm asking questions from these physical students, online students should remember that you also have the freedom to reply me. Okay. You can reply me simultaneously. Okay. That's it. Online students. Write it in pen. Write it by pen. What's the main scale? 5. Is it 5? Just before the cylindrical scale. Which it? What is it? Show me it. This is scale. So this is 1, 2 millimeters, 4 millimeters, 5 millimeters. So this is going to be 5.5 millimeters. So this is 6 millimeters. Just before the edge of the cylindrical scale. So it is 6 plus something. So you are going to is coinciding with this. What's this reading? 40, 41, 42. So you are going to add 42 here by multiplying it by 0. You are doing max or bio? Bio. No, no. You bio. You also bio. You to max. Two max people between two bio people. Okay. Roman number 2. Try it. Roman number 2. This is a fake pen. This pen is from Singapore. Okay, it's a good brand, Pilot. Okay, this cost almost 500 something. So here, this pen was here. Either this is also something. Shape is exactly like this. Okay, either this is also that sort of pen, and this is a fake pen. This exactly the model is same, but this red color is the fake one. If you see the pressure here, I can move this, so it's easy to write. The pressure is, I don't want to spend a lot much effort here. So in this pen, it's hard to write. So I thought if these two pens are same, if I exchange the spring, this is going to be softer, right? But when I remove this, the setup inside is really different. It's a cheaper setup. You have like, have you seen in some that these sort of pens, you have like this part in the pen tube, the ink tube, you have this part, and here is the, yes, we have the lock the spring, the pen's tip. Okay, but in here, but in gel pens, the system is different. Gel, these thick pens, they have something with the tip, they have a gadget, and they are going to fix the spring. So this is like that. This is something different. Take ease. Fine. What's the reading of the next part? It's going to be 5.47. It's easy to take reading, right? You don't want to calculate. Finish taking a reading. 0.25. 5 point. You try to the rest of it. 47. 10, 10. That ne? Okay, try to do other questions. You can do questions, right? You can do them until zero error part. So, fourth question, I have to tell you about the zero errors. Oh, whatever it can run, eh? It won't work for a phone on the smart board. You can write from a pencil. It's scratched. Fine. So you can take the reading. So let's go to, let's see what a zero error is here. Okay, what a zero error is. So zero error in the sense, this distance, which distance? This distance is going to be 0, but here this is not going to get aligned with the principal axis, with the datum. It's going to be here or here. Okay, take it. Cut a little. Okay, now aligned. Now there's no zero error. So this is 0, and if this is like this part is going to get aligned. If this is like this part is going to get aligned. Okay, so if this is moving downwards, is a one sort of zero error. If this is moving upwards, it's going to be another sort of zero error. Fine. So how many zero errors, type of zero errors do you have? 2. What are they? That's it. Positive and negative. Okay. What's the other name of positive zero error? Negative correction. The other name of negative zero error? Positive correction. So negative correction in the sense you have to deduce something, deduct something, deduct something. Positive zero error in the sense, positive correction in the sense you have to add something. Okay. So here we have to see how to recognize the negative or the positive part. Okay, fine. So think that this is like this, coinciding the 0 with 0. So it no gaps. Think this got worn out. Okay, I'll take a pink color. This part got worn out. Worn out. So this is now the nib edge. This edge is the nib edge of the moving jaw. What's the name of this part? The moving jaw. The name. Alvin. Next part. That's it. Spindle. Okay. The spindle. Spindle in the sense you can remember it. How did I? You get after you do some questions, you get familiarized with those names. So this is the nib edge of the spindle. Which part? I'll color it in red. This edge is going to be the nib edge. So the reading is 0, but this is not touched. Okay. So I have to touch it. Okay. So I have a distance between this, but the reading is 0. That's an error. Why? Distance between this should be the reading in here. That's the rule. The distance between this is 0. So we can move this again. We can move this in which direction? This direction. It's going towards it. So to move this towards it, which side should we rotate? This side. This is clockwise, or this way. This is anti-clockwise. Which? Anti or clock? Clock. Answer clock, people. Clock. Everybody's clock. So we should turn this clockwise. So when I'm turning this clockwise, what happened? This part, when I'm turning this clockwise, this 0 is going to go up. Okay, up. So if you can if you are going to recall this, but recall the vernier caliper, I said that this is the fixed part, this is the fixed part, and this pink color is the moving part. Pink color is the moving part. You can move this. Okay. So if there's no any gap, it's fine. So if this edge coloring by this yellow color, I'll take this is the edge. This is going to worn out. You can take it further. Take it further. So if this is going this direction, the 0 is of the main scale. This is the 0 of the vernier scale. If there's no any error, so this part can move. You are moving it further this direction. So this is in the negative part. This is the scale. It is in the negative part. So that is what error? Negative 0 error. So when it is going worn out, it's being a negative 0 error. So people, when the 0 of a vernier, where's the page? When the 0 of the circular scale is over this part, it's going to be a negative 0 error. What? Negative 0 error. So you have to add the stuff. It's going to be positive correction. Okay. So again, go to the tute. Negative 0 error. Positive correction. Fine. This is negative 0. Don't just go to the theory part. Just don't read them. Just don't read them. Just keep your paper, book like that. Okay. So you know the 0 error. How to find if it is negative 0 positive 0 error. If now you have turned this. Now since I have turned this red color is going to coincide with this. So again, what happened is there's no red color here. There's no this purple color here. Now this stuff. Right. So now it's like this coincided. There's 0 gap, but there's a reading. This reading is the negative 0 error. If you can remember, how did we find the negative 0 error? Negative 0 error, it's a special case. Why? If you are passing this line, you are going to coincide from this direction. From this direction in the sense, let's take white color. You are going to coincide from the 9th division, 8th division, like that. So you are going to take this reading, if it is 9, coinciding with 9, you are going to take the total number of divisions, it's going to be 10. So how you are calculating the 0 error? 10 minus 9 multiplied by the least count. That's the 0 error. That's how you find the 0 error of a negative 0 error. Fine. So likewise in this, which in when a 0 is going to get here in this part, which part? In a micrometer screw gauge, that's how you find it. Okay. That's another method to find if there's a negative or a positive 0 error. This is how you find it. So I said that when the 0 error is not there, this part is going to be like this. Wait. Okay. Okay, select this part down here. This row, let's see. Now select this whole part. Fine. I'm going to end like this. I have to work part here. Shapes. They have a solid shape. But can you see this color? No. There are no any colored shape. Can you make a scare from this? Erase. Write it down. That's not good. So okay, let it be like this. Fine, and select. So when there's no any 0 error, this is with the principal axis, but this is not correct. Why? This part is going to be like this. Like this. Okay. So part is going to be. So when it is coinciding the edge with the 0th of the main scale, this vernier 0 is 0. 2 zeros. Okay, fine, whatever. Let's erase this first. Okay, right. Now this is going to be like this. The two conditions, if there's no any 0 error, this 0th of the vernier scale is going to get aligned with the datum or the principal axis, and this 0 of the main scale is going to get into half. Okay, so this is when there's no any 0 error. Now assume that this part is worn out, that part is worn out. So what happened? I'm going to turn it in this direction. I'm going to turn it in this direction. Like this, I'm going to turn it clockwise. So this is going forward. Then this part, this part, this part is going to okay. So this part is going to get moved above like this. Is it? Yeah. Vernier scale is going to be like that. But what about the main scale? Now this whole part is going in front. It's going here. But the sleeve, I said the sleeve can move, right? Sleeve can move. That's to explain you all. But here the sleeve, in practically the sleeve doesn't move, because if the main scale moves, you can't take a reading with the vernier scale. Think if the main scale moves with the vernier scale, you can't take a reading. The main scale sleeve here doesn't move. Okay, that stays here. This circular part has a small wire, and that wire inside from this thimble connect to inside this sleeve goes inside from inside this sleeve and gets connected to this spindle. That's how the spindle and this part moves here and there, but the sleeve doesn't, because this but this is known as the thimble. Thimble is swallowing the sleeve. Understand? Thimble is like අත අරගෙන මෙයාව මෙහෙම දාගෙන යනවා. Understand? It's swallowing it. So when you turn this is going to go over the sleeve. So if there's no zero error, you can see half of the zero. If you are going to push it in this direction, the zero is going to gradually go inside this. This thimble is going to eat the zero. So if there is a negative zero error, this is how you are going to find it. You are going to see only a part of the zero, but a part of a zero. Okay, a part, when you can see a part of a zero, and if the zero is not aligned, that's a negative zero error. When you can see a part of a zero, and when the zero is aligned, that's not a zero error. Understand? Understand? So if you can see a part of zero and the zero is aligned, that's usual. That's if there's no any zero error. But if you can see a part of a zero, or if you can't see the zero and there is the zero is not aligned, that's going to be a what zero error? Negative zero error. Why? Because this thimble is moving in this direction. So if you take a scale, okay, you know this is 0, this is going to be positive 1, 2, 3. So this part is going to be negative, negative 2. So this thimble is going in the negative direction. So that's why we call this as negative zero error. Understand? So if that's a negative zero error, what's the correction? Positive correction. Understand? So we have in negative zero error, if we take negative zero error, system that we take the reading is different. How? We are taking the coinciding part, subtracting that from the total number of vernier division. So here you have total number of 50 divisions. So it is going to coincide 45, so 49, 48, 46, it's going to coincide from downwards to up. So if it's coincided with 45th division, it's going to be 50 minus 45. So 5. You have to add 0.05 to the final reading. Understand? Understand? Okay, fine. This is how you recognize a negative zero error. Okay. Now let's look into a positive zero error. Positive zero error. So this is usual, right? This is this if there's no any negative zero error, no any zero error. This is coincided. Okay, this is coincided. Fine. This color, yeah, pink color. Check this. I'm going to see. So that here, so I'm disintegrating part by part. Zero is part. Thing is, these are not straight. I'll delete this off. These are going to be a little bit slanted because this is a not perfectly cylindrical, a bit angular shaped. Okay. Now what I have to do is this. when you don't have any zero error. So I dripped this 0 in magenta because to distinguish it. Whole part. Now you can see the 0. Fine. This is when you don't have any zero error. Can you see it clearly, fine students? Is it clear? You want to zoom it? I can zoom it in the board. Okay, fine. Now let's focus into this part. What we are going to do is we are going to see the positive zero error. So negative zero error means the this spindle is going to get wasted or worn out. Okay, so what's the next part of the zero error? This is negative zero. Positive zero error means it's going to get rusted or corroded. So you are going to get an additional part. Okay, so you are going to get an additional part. So if there's an additional part here, just think there's a part here. So this part is going to move this side. So this total, if there's going to come an additional part, this whole system is going to move in this direction. Okay, in this direction. So assume that rusted part is here after this green color line. So you can't see the green line. So okay, now the picture. So this green color line after this particular part is the rusted part. Think like that. Okay, so before this is not rust, before this is, just think now it's not rusted. So 0 is coinciding here, 0 is coinciding. Okay, now if this get rusted, there's going to be a part additional to here. So there's something going to come in between this. Okay, so this spindle should move in this direction to compensate that value. Okay, understand? So now think that the part here is the rusted part. So rusted part is here, and now the spindle and anvil is still what? Coincided. But here should be the reading. Yes, there should be a reading. There should not be a 0 here. Why? Since this is going to move here, this spindle can't move alone, all alone. It's fixed with the thimble. So when it's going to move in this direction, spindle is going to move which direction? Clockwise, anti-clockwise? Outside, anti-clockwise. Understand? Anti-clockwise. Fine. So if this is going to move anti-clockwise, this part is going to be anti-clockwise, this direction. So this is going to come down. This is going to come like this down. So the 0 of the vernier scale is here. 0 of the vernier scale is here. 0 of the vernier scale is here. Understand? 0 of the vernier scale. Is that the only thing? No. Vernier scale is like this. So what about the main scale? What about the main scale? So if you turn anti-clockwise, only the thimble and the spindle is going to come this direction. But what about the sleeve? I said that thimble is something like swallowing a sleeve. Thimble is swallowing the sleeve. So when the thimble, just think like this. This is the sleeve, this is the thimble. So when the thimble is now here, now the thimble is moving this direction. So the sleeve is going to remain. So the 0 that is in half is going to come in its full form. Okay, so what happens is this 0 part, I should be able to move. Okay, this 0 part and this line. Okay, fine. It was in here previously. Now it's going to move here. It was here like this. Now, since the thimble is moving backwards, this is going to be here. Not the sleeve is moving, the thimble is moving backwards. To be more specific, if to understand this perfectly, we can do like this. We can do like this. See here, this is what's going on here. Now this is here, this can't move. The part that is moving is this. This color, this part, this 0, this and this part. This part is going to come backward here. Understand? Okay. So this part is going to come backwards, but still there's this sleeve. This sleeve is there. Sleeve is there. Understand? There's going to be readings here. Understand? So now what type of zero errors is this? So this edge of the stop for a second. So when this edge of the cylinder scale is moving in this direction, so these are positive numbers. So this is going to be a positive zero error. So the next name is negative correction. Negative correction. So we have to subtract that part. So it is easy to take a positive zero error. How? You are going to see which part is coinciding. For this example, let's see, can go. I can. Fine. So this 0 is going to come here. So let's assume that this is coinciding with this. So this is the first Vernier scale. So this distance is going to be, what's this distance? Distance between these two. The least count. The least count, not the least count. Yeah, the least count. The least count. Yeah. So this is going to be how much? When this is coinciding, 1 multiplied by the least count is going to be 0.01. So the negative positive correction, positive 0 error is positive 0, negative correction. Okay. So 0.01 should be deducted from the reading. Okay. You are going to take the reading. After that, you are going to deduce this 0.01 from that reading. So finally, you get the corrected reading. Understand? Okay. This is how a zero error in a micrometer screw gauge works. Fine. So that's all about zero errors. Positive zero error, negative correction, negative zero error, positive correction. So which one do you like? Positive zero error or negative zero error? Positive zero. Okay. The word is negative, so that's a little bit hard to work. Okay. You should remember like that. So positive zero error, it's easy to find, but negative zero error, you subtract the thing. A little bit more complex. Okay. Fine. Now let's complete the sentences in your book. Now come to the zero error of the micrometers page, page number 2. Page number 2. All right. So this is the picture, whole picture. So I guess the recording students can see that. They do something here. I was explaining. No, I was working here only here. Because I zoomed the camera, they can only see only this much shot. If I drew something there, it's going to, they can't see that. Fine. So zero error of a micrometer screw gauge when spindle and anvil are in contact. If zero division of the cylindrical scale does not coincide with the zero division, if it does not coincide of the main scale, then there is an error in the instrument. Okay, there's an error in the instrument when the zero is not coincided with the zero. There are two types of errors, positive zero error and negative zero error. So now let's look into what a positive zero error is. So when a positive zero error, when the spindle and the anvil touch each other, the zero mark of the circular scale is below the middle line of the linear scale. Okay, it's below. Why it's below? Because we are turning it anti-clockwise. So it's coming outside. So this is going to be below. Below the linear scale as shown in the figure. The zero error on this occasion is obtained by multiplying the number of circular scale divisions that coincides with the middle line of the linear scale. Middle line of the linear scale in the sense it's going to be the principal line or the datum line. You can call it those way. Right. So mark it in in the diagram. Here, take a pencil or a pen. Mark this line as datum or the principal axis. Principal axis of the main scale. Okay, principal axis of the main scale. Okay. So fine. So now is that online people tell something to write on the board, just take a screenshot, okay, as soon as possible. So there is a zero error. Each set coincide in the middle line of the linear scale with the least count. Okay. So the next easiest method to find the zero error is I have put that in here. Here you have a small box, right? Okay, this box. What's it? Read it. Read that box. If we can see the zero, it's positive zero error. So if we can the zero of the main scale, that is positive zero error. Okay, fine. So this is how you calculate the zero error. Which zero error? Positive zero error. Zero error is equal to zero error is equal to zero error is equal to what? Zero is equal to, you are going to find the number of Vernier scale divisions, line of coincidence, line of coincidence, line of coincidence, coincidence, coincidence or alignment, both are same, multiply by the least count. So you can mention this line of coincidence as the number of Vernier scale divisions. Number of Vernier scale divisions, that's coincide. So, okay, you can write that in the small box, right? Given reading has a greater value than the corrected value. Given reading has a greater value than a, so when you take a reading, let's assume that this diameter of the ball is 5 centimeters. 5 centimeters. Okay, 5 centimeters you can measure from a ruler. Okay, also you can't measure 5 centimeters. Then you have a positive zero error. This has gone inside. Okay, now it has a reading. When the anvil and spindle is meeting, there's no any gap, but it has a reading, and this reading is there. Okay, fine. So from here only we are going to measure the distance, and then now this distance also has a reading. Now the distance also has a reading, and that's the distance between these two. But since you have zero error, the final reading you take from the micrometer screw gauge is greater than the corrected reading. So this is going to be something 5.3, 5.3 or something. 5.3 or something. So this is not correct. You have to subtract this 3 positive zero error. You have to subtract this negative correction. By negative correction, you can find this 5 centimeters. Understand? That's what they're saying here. Hey. Something wrong. Did I explain? Huh? Online people. No. Now I changed the camera. Now they can see it. They can see it. First of all, when I was explaining that, I zoomed it because it was not clear. Now they can see. They can see that. So what I was explaining. Okay, fine. I thought physical students are the selfish, but no, they're thinking about online people. So don't worry. Fine. So the correct measurement is obtained by subtracting the zero error from the reading. Okay. Also, it can be called as the negative correction. Fine. So corrected value of the measurement is equal to reading subtract the zero error. Reading subtract the zero error. Reading subtract the zero error. Then reading subtract the zero error. Subtract the zero error. This is the this is the corrected value. Corrected value. Fine. So next, the zero calculation of the above figure. We are going to find the zero of the above figure. So how are we going to find it? So what's the coincidence? Line of coincidence. mark 5. Okay, that's 5. I mark it as 5. So this is going to be equal to 5 multiplied by 0.01 millimeters. That's equal to 0.05 millimeters. And they're telling to find the zero error. So negative by negative correction. So in exam papers, they trick you all. If they are telling write the zero error, you should write like this. Okay, fine. Negative zero error or positive correction. So it's going to be the opposite of this. Let's come into this. When spindle and anvil touch each other, the zero mark of the circular scale is above the middle line of the linear scale as shown in the above figure. So it's going to be above the middle line of the linear scale. So this part is going to be above the linear scale. This part is going to be above the linear scale. This is going to be like this. Sorry, that's going to be, this pink color is going to be like that. The pink is going to be what is this is going to be like this. Zero is going to be above the zero line, and as shown in the figure, the zero error on this occasion can be found as follows. So you can find this zero error as follows. How is it? What's the method? Number of vernier scale divisions. Number of vernier scale divisions. Where is it? The shortest form. It's here. Total number of division in the cylindrical scale. Total number of, so there's plenty of space. Total number of divisions in cylindrical scale subtract line of coincidence after that brackets. This is how you find the zero error. Multiply by the these count. Okay. So in the box, I have given a short method to find it. If we cannot see the zero, it's the negative zero error. If you can't see the zero, and if the zero of the vernier scale is not coinciding with the datum, that's going to be the negative zero error. Fine. I explained it before. The reading given by the instrument has a value less than the corrected value. Because it's the opposite of the zero error. Okay, think it. Hence, the screw gauge is said to be having a zero error, negative zero error. Therefore, it is known as negative zero error. Since the corrected measurement obtained by adding the zero error to the reading, it can be called as positive zero error. Okay, so corrected value of the measurement is going to be reading plus zero error. Simply reading, you can write this here, reading plus zero error. Not zero error. Wait. Corrected reading, zero error. Yeah. Corrected reading. So zero error calculation of the above figure. This is the corrected reading. This is the corrected reading. Corrected reading is going to be how much? Coincidence? 45. So 50 minus 45 multiplied by 0.01 millimeters. So this is going to be again positive 0.05 millimeters. Right. That's the zero error. That's the zero error. Under the box, you have a part to write zero error. Error. Good. Okay. So let's do a question number 7, Roman number 1. Question number 7, Roman number 1. So you can see the 0 as well as you can't see the 0. Only a part of 0. So uh, so the theory here is in positive 0 error, I have given a box. We can see the 0. It's a positive 0 error. See the 0. It's going to be a positive 0 error. But again, in the negative 0 error also, you can see the 0. Sometimes only part. Okay. So assume that as half of a 0 error. That's because manufacturing difference from each brands. So some brands will manufacture. Some brands will, if this is the 0th of the main scale, they will write the 0 like the center going from here. Some brands will write the 0 line and put that 0 this corner here. Okay. Some brands, if they are out of their mind, they are going to put the 0 here. Okay. That depends. Okay. Understand? So if the I'll draw this in pink color. Sorry, this color. If the edge of the cylindrical scale is going to coincide with the 0, that's going to be like this. So yeah, if there's no any error, you're going to see exact half. Exact half. So in this case, if this is going to coincide with the 0, if there's no any 0 error, you can't see the 0 in this brand. Okay. So in this brand, you can see the 0. So normally, generally, not specifically, but or most of the time, this is the brand that you're going to get in your exam paper. So not like in theory. So in the theory, what I said, if you can see the 0 error, you should write there. No, not write. You should remember that not the 0, exact 0, half. Take it as half. If you can see the half of the 0 error, there's no any errors. If you can see more than half, it's going to be positive 0 error. If you can see less than a half, that's going to be a negative 0 error. Don't write it. That's not an important point because that depends. So what you have to see is if this is the 0 errors line, if this is the 0th line, this line, you have to see this is the cylindrical scale's edge. You have to see if there's a gap. There's a gap. If there's a gap in the range here, the positive direction, that's a positive 0 error. If there's no any gap, and if there's no any gap, and if the 0 is half, if there's no line, you can't see any line. Okay, you can see only a part of a 0 circle, and they said that's an error. So that should be what is the error? 0 error, negative 0 error. Understand? That's the logic. Crystal clear? Fine. So what's the 0 error here? Seventh question, Roman number 1. Seventh question, Roman number 1. Let's find it. So you are coinciding which part? 20. You're coinciding 20, right? You're coinciding 20. So I'm going to find the 0 error. What's the type of this 0 error? Positive 0 error. Okay, positive 0 error. So the final part should be a negative mark, negative correction. Okay, positive 0 error, negative correction. Okay, what I'm going to do is 20 multiply by, what's the least count? 0.5 millimeter main scale divided into 50 divisions is going to be 0.01 millimeter. Okay, 0.01 millimeters. So this is going to be 0.20 millimeters. Understand? Do not calculate this. How 20 becomes this? So the 1 is here. So if you multiply this 1 by 20, the 20 should come like this. The first digit, the first digit. So that's how you write that 20. Simple. That's how you multiply decimal numbers by people. Fine. So B, in figure B, you have to, they have given the reading. Okay, in figure B, they have given the reading. Okay, I found the zero error. I found the zero error. Is the maximum. So the zero error is, zero error is negative 0.20 millimeters. Okay. What's the reading? Reading. Here, if you see the scale just before the edge of the cylindrical scale is 1, 2, 3. This is the 0. You have this 1, 2. You have 3. You can't see this part. This part. Okay. You can't see this part. So it's going to be 3, not 3.5. Understand? Okay. 3. So this is 3. You're going to write here 3 millimeters. 3 millimeters plus 3 millimeters plus, what's the line of coincidence? 5. 5 multiply by 5 multiply by 5 multiply by 0.01 millimeters. So this is going to be equal to 5 times 0. So this 5 is going to come here. So this is going to be, this is also in millimeters. So 3 is going to come here. So this is going to be 3.05 millimeters. Okay. Why people? Did you look in this? The 3, that's before the decimal point. That's before this decimal. Decimal point is here. So 3 is going to come into this digit. 5 is going to come to this digit. So it's going to be 3.5. Understand? That's why you are taking the reading directly. Understand? Line of coincidence 3. Line of vernier scale, main scale just before, that's 3. Line of coincidence 5, that's going to be 3.5. 3.05. Understand? Because the least count is 0.01. Fine? Right. Should be fine by now, because we are again recalls. So this is the reading. So is this reading correct, people? Is this reading correct? No, the reading is not correct. So what should we do? Subtract. Should subtract. So to be more specific, you can put a bracket because you can confuse this equal marks and negative marks. So what I'm going to do is I'm going to find the corrected reading. You should write corrected reading. Corrected reading. Write that here. Okay, corrected reading. So this is going to be 3.05 millimeters. Subtract 0.20 millimeters. So this is going to be equal to, this is a little bit hard. That's it. It's going to be 85. What 85? 28.5. How did you do that? Just assume there's no any 5 here. Okay. 3 subtract 0.2 is going to be 2.8. After that, add this 5. It's going to be 2.85. Understand? 2.85. 2.85 millimeters. These are tricks, huh? You should know this if you have passed scholarships. Who have passed the scholarship? You? No, you. No, school? Private school. Private. So your A level, O level doesn't depend on your scholarship. A level doesn't depend on your scholarship plus O level. Your university doesn't depend on your A level, O level, and scholarship. Just are independent. That's just for a time period. Just for a time period, that's going to stand up. So the pattern is, if you fail scholarship, you're going to pass O level, and after you pass O level, you're going to fail A level. If you fail A level, and if you enter the university, you're going to be a good student at university. Okay. So you have to maintain the consistency. That's really hard. That's really hard. Okay. So that's the corrected reading. So now let's go into a negative 0 error. Go to question number 7, Roman number 3. Question number 7, Roman number 3. Question number 7, Roman number 3. Oh, tell me what's the 0 error? 0 error. The 0 error. Zero error. No replies from the online people. You're not doing the question. This one. Can't remember. Elomi Nanayakkara. Is it? Find it. Question number 7. Roman number 3. Online people. Students. Are you there? Sleeping? Nope. You're not sleeping. Yeah. Okay. But you're not listening. Listening. Doing it in 3 minutes. Why? Why do you need 3 minutes? Okay. Tell me the reading. Yeah. Question number 7. Roman number 3. Okay. Okay. Question number 7. Roman number 3. You should be alive. Okay. In the online session. You also. To come online, you should reply the questions. You can turn on your mics. And if I don't see the message, sir, read my message. The thing is, sometimes I mute my mic. I mute my speaker. I won't hear it. Okay, so that's it. That's it. I'm doing it in now, and it only. Wow, confidence. So line of coincidence. That's 35. But can we write 35 here? No. 50 subtract 35 multiply by 0.01 millimeters. Okay, fine. So 35, 50 minus 30 is 20, 20 minus 5 is 50. That's how I do sums. Okay, so since I do part by part, I can do it faster than others. I mean, for these stuff, it's really easy to find it, but when it's going to be a real hard calculation, others take time. I don't take time, right? Because I'm adding it part by part. That's easy, né? 50 minus 30, everyone knows that's 20. Now 20, you subtract 5, that's going to be 15. So 15 millimeters multiplied by 0.1. Now I don't want to write the units, right? This is second step. Here also, I don't want to write it. I don't want to write it. Now this is going to be equal to 0.15 millimeters positive. The negative correction, why is the negative correction? You can't see, it's barely, you can barely see the zero only at this mark. This is originally from a micrometer screw gauge. I mean, a stimulated micrometer screw gauge. You know, stimulated virtual micrometer screw gauge. I took screenshots and part by part I added this document. Okay, so it was really hard. It was really hard. It was taking a lot of time to make this question tube. Okay, so 15, this is going to be 0.05. 0.05. Now let's go to the reading. So 0 error is plus 0.15. Is it? I forget stuff. Is it? Read. So the reading is, what's the main scale division just before the edge? Here you have 1, 2, you have 3, and you have this part. So this is going to be 3.5. Understand? Why it's going to be 3.5? Because in your circular scale division, you have only 50 divisions. If you have 100 divisions, they won't give these marks. Understand? Let's go to those type of questions. Then you can see this is going to be 3.5. 3.5 millimeters plus 0.15. Yes. Oh, the least count. What's the line of coincidence? 45. So 45 multiplied by 0.01 millimeters is the substitution part. So you have to add the units. So after that, you can do it directly, or you can do part by part. 3.45. Now this 45 is going to come here. 45. So if you add 45 to 50, 50 plus 40, 90. So 5 is there in the last digit. So this is 3 point. 3 point. Yes, yes. No, it's fine. So, but yeah, you. 3 point. Right. Because here you have a 0 here. Don't get embarrassed. Don't get right. She's coming her face. Don't get embarrassed. 3 point. This 50 and this 45. This 45 is going to come here. 0.45. So 0.45 with this 3.50 is going to be 50 plus 40, how much? 90. 50 plus 40, 90. So this 5 is going to come here, 95 millimeters. Is this correct? Right. Now let's go to the corrected reading. Corrected reading, this is going to be equal to, so we have 50 minutes. So I plan to do a structured question from A level. So since there's only 50 minutes, let's go directly to MCQ question. Okay, 2021. So this is going to be 3.95 millimeters plus or minus, plus 0.15 millimeters. So this is going to be how much? So how are you going to do this? The easiest way, you can add this 10 here and go. It's a little bit hard. What I'm going to do is I'm going to add this 5 here. So it's going to be 4.00. Then add the 10. Then it's going to be 4.10. Find the easiest way every time. So do I want to mention this 0? I have to mention. Why? I said that since this is the last digit and it has a value when you're taking measurements from a instrument. Okay, we are taking measurement from an instrument. So I don't think, but mostly you will get reduced. Marks will be reduced if they look from point by point. So like these questions are going to be barely in the MCQ, not in the structure. Okay, fine. So let's try to do the MCQ, and if we have time, let's move on to the structured question. So go to page number 9, page number 9, 2020 MCQ, 6th MCQ, last MCQ. Now it's been 6 years after 2020. There's only one question, I guess. So from micrometer screw gauge. So figure A shows the scale of a micrometer screw gauge when the spindle and anvil touch each other. So it's going to be a 0 error. When it's touching, it should be 0. But if it's not 0 error, correct it is 4.1 millimeter. 3 point, fine. Correct, but not super correct. You should mention it as online people. I'm talking to you. 4.10 millimeters, as I mentioned before. So figure A, you can find the 0 error. Figure B shows the scale when a metal sphere is properly placed between spindle and anvil. The pitch of the screw is 0.5 millimeters. The circular divided into 50 equal divisions. Then find it. So first of all, before finding the 0 error, what should we find? The least count. Okay, let's go step by step. Least count. Let's go to least count. So least count is going to be equal to pitch divided by n. This is going to be 0.5 millimeters divided by 50. So this is equal to 0.01 millimeter. Fine. So I'm going to take from the figure A, I'm going to take the 0 error. So I can see the 0 clearly. So when you can see the 0 clearly, you're moving this direction. So this is a positive 0 error. So that's going to be a negative correction. I put a negative mark. Okay. So what's the line of coincidence? 4, 0, 1, 2, 3. Is it 3? Yeah, 3. 0 error. That's 3. So 3, you multiply by 0.01. 3 multiplied by 0.01. That's going to be 0.03. 0 error. Fine. I'm going to take the reading. So reading is going to be equal to, from figure B, I'm going to take the reading. From figure B, I'm going to take the reading. Figure B, I'm going to take the reading. The reading is 2, 3, and the downwards line, that's going to be 3.5. So 3.5 millimeters. Add 2. What's the line of coincidence? 31. So this is going to be 0.31. I wrote it directly. Understand? 31 multiplied by 0.01. That's going to be 0.31. Okay, fine. If you want, I can write it in a direct way. So we should have a progress, right? 31 multiplied by 0.01 millimeters. This is going to be equal to 3.5 plus 0.31. So this is going to be equal to 3.5 plus 3 is every times 8. So 8.1. This is the reading. So they are asking the correct diameter. So let's come to the next part. I'll put a star mark. correct reading is equal to negative 0 error. So this is an equal mark. This is an equal mark. So this is going to be what? 3.81 subtract 0.03. 0.03. So what I'm going to do is I'm going to part this to two parts, 0.01 plus 0.02. Okay. Subtract. Why did I make 0.01? Because I can see a 1 here. So this 81 minus 1, that's going to be 0.80. So subtract 82 from 80, that's going to be 78. So this is going to be 3.78. Is there an answer like that? Is it? The answer is going to be third answer. Okay, third answer. Positive 0 error, negative correction, reading, subtracting that from the reading. So we got this answer. We got this answer. This for bio people. Why do I mention every time bio people? Because they are not doing frequently calculations. So they should know some simple methods. So these simple methods, they born when you are doing, they are not coming from your birth. Okay, that's when you practice questions. So max people, they will gain that knowledge when they are doing questions. Okay, especially in frequency distribution lesson. That's a lot of stuff to. You have to add a column and multiply that by another number and again take the addition. That's going to be normally 20, 21 data. You have to add them. It's going to be really, not really hard. I love adding and subtracting. I hate because did you see that? If the number is going to be this digit is going to greater than the last digit of this, it's going to be a little bit complex. I mean, that's complex for me. So I make it simple, subtract, I get the answer. So this is 3.78 millimeters. Okay, so MCQ done. This 20th question. You can try the other MCQs. Okay, I have given you two model MCQs and other past step MCQs. Okay, so we can only 10 more minutes. We can do a structure. Okay. So structured questions. Go to page number 5. Let's do a part from the structured question. Question number 1. Structured question, page number 5. Question 2, page number 5. Okay. Name the parts of the micrometer screw gauge labeled A, B, C, D. You are going to name it. Name the parts of the tables. Part labeled of the micrometer screw gauge. A. What is A? Main scale. Is it main scale? No. What's it? Sleeve. That's the sleeve. That's the sleeve. Sleeve. But have I mentioned this before? When they are making they make a solid marking scheme. After that, I said they are choosing one random paper. Have I said it before? They're choosing random paper and they're seeing how students have answered. So if they see they made the marking scheme for sleeve, they saw main scale. What they do is they integrate that part. So you get marks if you have main scale also. So when there's a confusion in any questions when you're doing the papers, don't get upset because they compensate them. Okay, don't get upset. So B part. So they are super talented students. Okay, I was a student like those. I was a student like that those days. They feel if they can't do a question, they feel that there's an error. Okay, I have felt it. If when you are doing questions, past paper question, you will feel it. So most of the time, there's no errors in past paper question because that's a question for the whole island. Okay, but sometimes if there's an error, it's really hard. I have worked continuously for 2 weeks for one question, for one MCQ question, and finally I found it. When I found it, I was because I based a whole, but that was worth it because I searched a lot about those questions. Okay, that's worth it. And so what they do is if there's an error in the question, the marking scheme, let's say the 5th option is the answer for the MCQ. What they do is for the let's take 21st question. So what they do is cut it. So sometimes they give for this and so second one you give the answer, but if there's a error in the question, they are going to give all. I love this. So every time if you see all or this sort of things in the pace row marking schemes answer sheet, that question is a damn question. I mean, those questions are prepared purposely. Okay, so most of the time the pattern of a physics question, MCQ question is physics is super beautiful before 2023. Okay, because it was hard. Like here 2024 or 25, I can't remember. A sir known as Dr. Rosa, a professor. Okay, he's a super sir. I mean, that professor, he can describe things very beautifully. Okay, the thing is, he simplifies the paper. He came to the paper crew, he simplified the physics paper. Now the Z, normally the Z score was highly ranked by the physics paper compared to other papers. So if you have a good marks in physics, your Z score is going to go that much up than you have a good marks in bio or chemistry. But nowadays, if we take bio stream, last paper, 2025 paper, bio have the bio has the highest Z score and the max has the highest Z score. That's why I got 90th rank, because I had a B in max. Understand? If there were people who had 2 A's and B's before our batches who were in the rank of 40, 50, 20, like, because max B in the sense that's going to get a little bit affected. So if that was in the highest Z score, let's assume that's physics, so that's going to, the rank is going to decrease. They give the rank not to the marks, they give the rank to the Z score. Okay, fine. So what I'm going to say is these questions are to challenge talented peoples. Okay, so talented peoples, they can do questions in a short time of period, like island first or something. Island first, island second, the top 10 is if he's island 10 in the sense he's have the exact knowledge of the island first. Small the fourth decimal point of the Z score is going to get differentiate. 2 point it's going to be 3.9006, and the next one is going to be 9.00. Right? Fourth decimal place. This is island first. This can be island third. Sometimes there are people who have the same Z score, so the exam department has to find this Z scores. Fifth, sixth decimal. Usually they find only to the fourth Z score, fourth decimal point. It's a beautiful thing when you go to the flying class. There's a level above the cloud. Go to that place. That's really beautiful. Okay. So the second part is the what's it? It's the thimble or the Bernie scale. It's going to be the circular edge. Oh no, they have said circular or the cylindrical scale. Circular, the cylindrical scale. Not thimble. Why it's not thimble? Because they have given another place to mark thimble, right? So this is going to be the circular or cylindrical scale. Cylindrical scale. Cylindrical scale in the marking scheme. It's given like this. Cylindrical scale. Third part, it's C. C is going to be, but that has only one word, that's thimble. Here don't write like this as 3 O main scale. In the final paper, you should write one of these, not both. Okay. So I'll say that in the marking scheme, sometimes let's take 11th question, they give marks for second option and the fifth option. So they give marks if you have marked second, or they give marks if you have marked fifth. So if he's a Pandita man, this 2 is correct. If he's going to cross both of these, he's not going to get any of the marks. Understand? You can't do like those sort of question. One, oh, you know one of these is correct, man. So write one. Can't write two. Can't be max ultra pro. Just a pro. That's enough. Okay. Thimble. And the fourth one is D. D. So D is ratchet, or sometimes some tuition goes, oh, I think not in the resource book. I haven't seen that word in the resource book. So mostly before the syllabus was born in the resource books, they use ratchet. Or they use this word, thimble head. Okay. For now you can write both of this, but I don't know. Write one of this. Okay. Write one of this. With another pen, you can write, this can be thimble head for your further purposes. Okay. So it's 11:59. So try these questions. It is easy here from B, Roman number 1, Roman number 2, Roman number 3. They are easy, really easy. So Roman number 4. So Roman number 5. What is the precaution taken in the micrometer screw gauge to avoid the overpressing the object? That's it. What is the precaution taken in the micrometer screw gauge to avoid overpressing the object? So every time at the final part of the structured question, they are going to ask a descriptive question. So why? What? Just tell me in your English. Why? What are you doing? You tell me. Do you understand the question? No. Did you understand the question? You? No. Understand? Understood. So what's the reason? Overpressing means, what's the meaning of overpressing? Oh my god, my handwriting is that much uglier. Look it from the back. So I said that we keep the fixed one here, keep the ball here, and we bring this spindle closer to this, but we won't push it further. Why? Because it can overpress the object. That's the word, overpress the object. Okay, if that overpress the object, a part of this is going to be wasted and a part of this is going to be wasted, and there's going to be an error. Okay, for that you don't use the thimble, you use the thimble head, or we can call this as the ratchet. This is a badass name. Just not like thimble head, that's like an old vintage look name. Ratchet is okay. Ratchet. So what the statement you have to write there is, let's take a small bit of time. Okay, online people. Turning by the ratchet, I think that space won't be enough. Okay, so write in a small font size. Turning by the ratchet after the spindle get closer to the object. Turning by the ratchet after the spindle get closer to the object till a tick tick sound is heard. Till a tick tick sound is heard. So for your further understanding, you can write in another color of your pen. Mark. The thimble head gives a quick sound. Okay, you can write it as a crick, click, or tick, or ticky ticky, whatever the sound. Okay, TikTok, don't write TikTok. Okay, the thimble head gives a crick sound when it is pressed enough. And it stops further pressing the object. When it's pressed enough and it stops further pressing the object. Pressed enough and it stops further pressing the object. The thimble head gives a crick sound when it is pressed enough and it stops further pressing the object. Okay, so when you go to your school, you're going to do the practical. Okay, so in between questions you have to answer. I gave the description, so this is a little bit hard question, that's why I gave the answer. So these questions you can write by your own. So I will give the answer scheme. Okay, so done for the day. So go to your home, revise the question, revise your tutes, revise your knowledge, do the questions. Now you have the question tute, you have the vernier caliper tute, you have the micrometer screw gauge tube. Other than that, I said you have to complete a part in practical tube. Can you remember? We did that deriving absolute error for a cube. Okay, I gave you space, and I said to do a circular scale part, calculation on a circular scale part to find the least count. That part, those questions you have to complete. Until now, you should be perfect. You should complete every questions. Don't keep any spaces. I was a people like that. But again, this is the beginning. Okay, you should be perfect. But if let's think you are in the middle of your grade 13 or something, if there's something to complete, don't take your time to complete those stuff. You have to go furthermore. Understand? Like, I'm a perfectionist, I say that. Before this year, I was a perfectionist. I mean, I need everything to be perfect. If there's nothing perfect, I I I don't do that thing. I don't that thing. It's bad. It's a bad thing. It's a bad thing. So most of the time, if you search about perfectionist, it's bad to be a perfectionist. Okay, don't make your mind to complete everything. It's better, but if you can't do that, leave it. Leave it. Okay, don't force yourself. If you can't do that, go near to the perfect. So near perfection. So that's the word of Arham. Okay, he says we should be near perfect. I can't remember the exact slang. He says nearly perfection or whatever. When you are doing papers, she will tell that word. So you can't be perfect. Sometimes you can, but try to be perfect. Okay, fine. Done for the day. Goodbye. Let's find out this.